Hello. Sorry, I had a weird mic hiccup. Cool. Okay, cool. Sorry. I had a weird mic hiccup. Hopefully y'all can hear me. If you can't hear me, just let me know in the comments. But yeah, welcome to today's live stream, or creative stream. And so Uh, today, if you saw the tweet or if you were in yesterday's live stream, what we're going to be doing today is we're going to be building a fun little interactive loading screen for a website or web application. And it'll be a little different than probably ones we've done in the past, where we'll be using React. And specifically, we'll be using a Next.js application. But we won't be using the React runtime. Instead, we'll be using the low-level WebJS runtimes, or I guess we call them like the advanced APIs, if you will. And really, what those APIs do is it allows you to build your own render loop and control a lot of the things that the normal high-level runtimes do for you behind the scenes. And so, in this way, it gives you a little more granular control, and we'll kind of go over what that looks like. And it's kind of a preview of what you can do to create multiple instances of artboards, dynamically creating those. We'll be working with dynamically created bears, um, and see how you can propagate this, not just for web, but a lot of our other runtimes have this kind of concept of a low-level API as well, such as Flutter, Android, and some others. And so it's a good insight if you haven't, if you're not familiar with any of the low-level runtimes yet, or you've played with the high-level runtimes and not really sure, how the low-level APIs kind of work. Um, it can look a little intimidating, but we'll try and make a super simple example today so that it's a little more accessible and hopefully a little easier to use after this. So, um, all right, yeah, I'm gonna start off with just showing maybe what we're actually going to be building as the end product. So let me change this real quick. We've got this loading screen. Just posted this on Twitter like an hour ago, but you can imagine something's loading. Probably takes a long time. I used to work in like insurtech startup, and there was always a loading screen that took like 2 minutes because it was like trying to underwrite someone in insurance. Anyway, it would have been really nice if we had like a super cool like interactive loading um, screen and animation to kind of go along with that. So this is kind of helpful in this case. This is just a fun little example that we built, but you can see there's like different kind of bears being generated and rendered here, some with different facial expressions and walk expressions. This is all work by Robert. And then we've got also this kind of swaying forest that I think we actually went over in one of our Tuesday live streams in the past, just to kind of show it off as a really cool example from the community. And this one's from Andrew Bellart. And so these are both in the community. You can check them out. Let's see. I want to actually share my whole window for this. Yeah. So this is the community asset for that forest. It actually has some like interactive bits here where you can click on the trees and some little birds come up. And so I remixed this mainly just to push the scenery down so that it lands at the bottom of the canvas, or the artboard, sorry. But really nothing else changed here. And so it's just an idling state machine. They've got some trigger inputs, but I think they should all be triggerable via listeners. And then the other one that we're looking at from the community that we're going to be building is this walk cycles one from our very own Robert on the creative team. And so he built this, looks like November last year, and there's probably a walk cycle tutorial on how to build these bears as well if you're interested. So you can find this on the community as well. And here, what did I remix? I think I cropped the artboard um, so that it's really only encompassing the bear and just a little padding on the sides of the bear. I think the artboard was a little larger. And so in this case, yeah, I'm just messing with the artboard space a bit. But you can see here, I'll try and zoom in a bit. Um, it's got the state machine with a walk type. And so this is a number input, starts with 0, and it looks like, this is actually another thing I remixed on the state machine is uh, for the state machine, there are different walk animations, and then I'm using an any state to essentially um, make a transition between all these different um, walk animations. And so I'm kind of enumerating them starting from 0 to 5. So if I do like 1, 2, 3, 4, some of these are probably similar actually, 5. Um, so, okay, cool. Yeah, so we got that going. Just checking. Sweet. All right, so yeah, these are the simple state machines that we're going to be messing with. Um, and you can find more docs on like how to use these low-level APIs that we'll be working with in our help docs. So if you go down to the runtime section in the navigation bar under WebJS, low-level API usage, there's this document that kind of goes step by step on how to construct your own render loop, which is really the main goal of why you would want to use these lower level APIs. So it's a little more code, a little more involved, but you'll kind of hopefully see the power of it when we get started here. Great. Okay, so actually jumping into the code. I'll share my desktop now. Sweet. Okay, zooming in a bit. I already noodled with this, of course, because there's a working demo here we've got. So just mainly going to be recreating this for the purposes of today. So the first thing I want to do, I've already created this scaffolding Next.js app. You can look on the Next.js docs if you're unfamiliar with how to do that, how to kind of scaffold a project up so that it has a lot of the functionality out of the box for you, such as routing, and plugins and your package setup and things like that. And so the two things that I also included, actually, let me take a step back. For those of you maybe unfamiliar with Next.js, Next.js is kind of a framework for building React applications, and it has a lot of out-of-the-box things for you, like I mentioned, with routing, server-side rendering, and it just has a really nice developer experience for kind of taking React to the next level. But for this main purpose, really all we're going to be doing is using React things and less so like advanced Next.js features. So we won't focus too much on that. But the two things I want to note here is where you start in your Next.js project is, in my case, I npm installed two dependencies, the high-level web runtime, which is Rive App Canvas, and then the low-level runtime, which is Rive App Canvas Advanced. And so we'll kind of see how we'll be intermingling the two. You could really just work with Canvas Advanced here, and that guide in the help docs kind of goes over that. But for this case, I really just wanted to make things simpler and kind of combine the two. And so we'll take a look at how we're doing that. The next thing is to actually get the assets for the app we're going to be building. So for the first one, I'm going to go ahead in our editor, go to download for runtime, and it'll download this forest riv file. So I'm going to pull that in the forest riv. And same thing with the bear. Downloading that riv file, and I'm putting it in my public folder. And the reason I'm putting it in the public folder is because I can treat .riv assets like any other asset I would include and bundle in my project, such as images or font files, videos, whatever it might be. They're incredibly small, and the nice thing about putting it in the public folder is that it's bundled with the application when you do the final build. And when you deploy the application, everything should be publicly accessible at the root of your website. And so if I were to deploy this at bearloading.com, I would find the forest.riv asset at bearloading.com/forest.riv. And so that's going to come in handy when we try and instantiate our Rive file. But cool. Okay, I've got my two Rive files. And just to kind of go over the start of where this app begins is this layout component. You can see it's kind of instantiating that HTML and body element. And this is out of the box Next.js stuff. So nothing really extra to code here if you've generated a new Next.js app. And where we're going to start introducing things is this page.tsx. And so with the new Next.js conventions, page.tsx, there's like a convention where this is the actual page that will render at the root of whatever folder you're in. And so this, because this is at the root of the app folder, this is just going to load at the root of my URL. And I decided to take out a lot of the boilerplate it already included and include these two elements. So I've got this loading text centered and this div, which encompasses a canvas element. And also for CSS, it's using Tailwind CSS, which is a utility CSS library for adding styles pretty easily to, in this case, my React components. And so you can look more on Tailwind CSS website and documentation if you want to learn more about how to kind of, if some of these styles look really strange, basically. But just to kind of go back to what we're going to be building, we've got this centered text here that's bear with us, and then it's loading, it's incrementally simulating some kind of loading progress. And so that's kind of what I've added here. I've got some state variables, PCT, and I just took this random algorithm off the internet that's simulating a loading progress. And yeah, I won't really dive too much into that other than it's every 100 milliseconds, it's updating loading progress number. And as it gets closer to 100, it slowly loads. So just to give that effect anyway. So once we have like this, this use effect that's continuously updating this PCT variable, as you can see here, what I'm doing is I'm passing it as a prop to this loading text centered component that I've created. And so loading text centered is, where's my loading text centered? Oh, here. It comes from this loading text component. And this is a pretty simple function component. Basically, it's just returning markup. And it's using a lot of that Tailwind CSS to basically center this bear with us h1 tag. And also this h2 tag with the percentage loading. So that percentage that I was passing in from that page component, I'm just rendering it here in that h2 spot. And so basically nothing too fancy here with this component. It's just centering the text in the center of the screen and updating it, the loading text as percentage comes in. So that's what that component's doing. Going back up, I've got my page component, and we have this div container element and this canvas element. And you can see I'm passing some refs here. What I want in this component is to have refs to the actual div and canvas element so that I can manipulate them. And we'll see why in a bit. What we're going to be doing and the way we're going to be using the low-level API is we're going to be using it in this. It's not really a component. It's more of just its own JavaScript class. is this. I'm going to create this class called Rive Orchestrator. And this class is really going to orchestrate all the different moving parts of building your own render loop. So here I've got some commented code. Uh, you can kind of see here that we're going to initialize the Rive file in renderer, and then we'll go over the various parts to building the actual render loop. So kind of starting out here. Um, I want this Rive orchestrator to have a canvas and container element. And so this is actually going to be the same elements that we've built in our page component here. We're going to be passing the references to these elements. So this div is like the container, and this canvas is the canvas element. So just keep that in mind. Yeah, so when I create the Rive orchestrator in page.tsx, which I'll do a little later, um, I'm going to pass this Rive orchestrator the canvas and container ref. Okay, so now, view my notes. Okay, the first thing we're going to do is we're going to instantiate Rive. And here is where I'm actually going to be using a mix of the low-level and high-level runtimes. For now, I'm going to import something called runtime loader. Um, from the high-level runtime. That's right at canvas. I guess while I'm here, I'm also going to include some things that I'm going to be using later. So we're going to be messing around with the layout a bit. The other thing I want to import are things that I want to instantiate for the render loop. So in this case, I'm going to be instantiating a renderer, a artboard, and a state machine instance. And so I'm going to go ahead and import all of those. So I'm going to start with artboard, the state machine instance. I'm going to import the canvas renderer. And also the main Rive API point for the low-level runtimes is Rive canvas. And I'm just going to rename that as Rive canvas type. And I'm going to import this from the low-level package. So that's Rive app canvas advanced. Cool. All right. So let's go back into this init. This init function is async because I want to await loading the file and the render. There's kind of a sequence of how I want to load these things in to make sure that, for example, we're not invoking a state machine input before the file is even loaded, things like that. So the first thing we're going to do here is we're actually going to create a private variable called Rive. This will be the Rive canvas type. And so I'm going to say this.rive is equal to await runtime loader dot await instance as Rive canvas type. And really what this is doing is behind the scenes, this is using one of the high level imports that we took in, the runtime loader. When we do runtime loader.await instance, this is a singleton that's essentially calling in and loading the WebAssembly file, which is hosted on package for this specific runtime version. And the WASM file is really what bridges our much lower CPP runtime, C++ runtime. And there's essentially this WebAssembly file that kind of creates a binding from APIs on the C++ side to JavaScript, which we're going to be using today. And so if you're unfamiliar, WASM, or essentially WebAssembly, is basically going to act as our bridge from JavaScript to the C++ APIs. These C++ APIs actually power all the APIs for example, our iOS runtime, our Android runtime, React Native, as well as some other ancillary runtimes that we've got going on as well. And so that Rive CPP is really the core of things. We are telling this runtime loader singleton to, hey, go load that bridge, that WebAssembly file, so that I can get access to those C++ APIs. And that's all going to be stored in this one object called this.rive. So everything that we kind of do stems from this WebAssembly file. The next thing we're going to do is we're going to create our renderer. And so this renderer is going to be responsible for orchestrating all our draw methods and paint methods onto the canvas element. So Rive draws onto a standard HTML5 canvas element. And the way you draw onto that canvas element is with a certain renderer context. In this case, we use by default a canvas 2D context. Given by the name of this package, Rive app canvas. And you can think of this kind of as like the paintbrush, the render, the canvas 2D context, that's like the paintbrush for the canvas. So I'm going to actually create a new private variable for the renderer. This is going to be the canvas renderer type that I imported. And the way we create the Rive specific renderer that we're going to be using to build Rive content or draw Rive content is using this.rive. So that thing that I just instantiated and awaited. There's an API on this called make render. And there's one property you can see it takes. It takes a canvas element. So if you're familiar with the way you actually get a canvas 2D context, it's dot get context on the canvas. And so this is essentially doing the same thing. We need to pass it the canvas element so that it knows where to associate the context with. And so this is going to be this dot canvas. Cool. All right. So I've got my main Rive API like head point. And I've also instantiated my renderer. Now I can start instantiating my Rive files. And once I instantiate my Rive files, I can start to pick from those Rive files like what pieces I need. So like what's the artboard I need? What's the state machine? Again, in the high-level runtimes, this is pretty easy because all you do is when you instantiate Rive, you just say like artboard, new artboard as a string, or state machine names and state machine one as a string. And basically the high level runtimes do a lot of this stuff for you. This is what it's doing behind the scenes. So we have to do this a little manually. So now let's instantiate both that forest Rive file as well as the bears. So I'm going to start with the bears Rive bytes. We're going to load the Rive file in as bytes. And so I'm going to do await fetch new request walk cycles.riv. So I'm making essentially a request at the root, or essentially the thing that I stuck in my public folder, that walk cycles.riv. So this is the bears file. And I'm going to call and then I'm going to set this as an array buffer. And I'm going to do the same thing for the forest Rive bytes. So this is forest.riv. Okay, sweet. So what do I want to do now? I'm going to actually create a reference to these Rive files. So I'm going to say private errors file. File. Oh, wait, no, just a file. I'm actually going to import this in my advanced APIs package. I'm going to set what is this dot bears file is equal to bears Rive bytes. Oh, wait. Actually, there's one step I need to do here. Okay, so I have the bytes that I loaded in from the Rive file, so I fetched that in. Oh, now I need to actually create a Rive file itself. A Rive file is an API on the low-level side. And so I'm going to instantiate this by doing await this.rive.load. So I'm loading in some bytes to create a Rive file instance. So I'm going to use uint8 array, which is how I'll parse the bytes. As file. And then this dot, I'm going to create the same thing here. Private forest file, Rive file type. Forest file is equal to await this.rive.load. So I'm creating a new Rive file. uint8 array. And it's going to be forest Rive bytes. Okay, so now what have I done? Just to recap, I've created my main entry point into the Rive APIs and storing that in this.rive. I've also, from that, created a renderer and stored that in this.renderer, and we'll use that to basically draw into the canvas in a bit. Next, I've actually loaded in those Rive files and loaded those in as an array buffer. And from that array buffer, I created a specific Rive file like instance and store that in bears file and forest file accordingly using those bytes. Some comments. Just really quick on this topic, is there any difference between using the runtime dot await instance from Rive App Canvas or Rive App Canvas Advanced? So runtime loader does not actually exist in Canvas Advanced. What you'd have to do is manually grab that WASM file. So really quickly, let me see if I can grab my WASM file. Just going into the Rive WASM runtime a bit, you're going to take a look at runtime loader. So this is a class, again, this is a singleton. And so the high-level runtime, which I'm looking at right now, this has that singleton runtime loader, which I was just working with. And when we called await instance, it's basically we're trying to resolve a promise, but really what's happening here is it's making a call to the WASM file where it's hosted. In this case, we have a WASM file hosted for each version of the runtime that's released. So, for example, I think we just released Rive App Canvas 1.2.0. And so this URL will be specifically for the WASM file at 1.2.0. Essentially, there's like a new WASM file. You want to correlate the WASM file to the version that you're using for that runtime. And the reason for that is because in some cases, we basically take in new changes from that Rive CPP runtime, that underlying base runtime for all that powers all our runtimes. And if those have new changes, we want to make sure that when it goes upstream and these upstream like JavaScript runtimes are consuming that through WebAssembly, we want to make sure that they're kind of in sync so that JavaScript is using the latest version of the CPP runtimes and nothing. For example, if you're on a much older version of the web runtime, we don't want you using the latest WASM file of the latest, JS runtime because that could have breaking changes. It could have newer, backwards incompatible, kind of ways of instantiating things behind the scenes, and so there could be a little bit of a mismatch. So the high-level runtime takes care of a lot of this for you. While in the Canvas Advanced runtime, you'd have to actually make the call to either where we host this WASM file or host it yourself on your own on your own application. And so I think in the docs there, it goes over kind of how to do that from the Canvas Advanced side rather than the high level side. So not, it basically shows you how to go about doing it so that you don't have to use runtime loader from the high level runtime. Yeah, hopefully that helped answer your question. Sweet. Okay, so I've got my Rive file instances. Now I want to actually create my artboards. So I'm going to start with actually maybe just displaying the forest artboard. So I'm going to do create an artboard instance by doing forest artboard is equal to this dot forest file dot um, artboard by name. So I can grab an artboard by name. In this case, it's new artboard. I can verify that just by going here. And yeah, there it's only just one artboard, so new artboard here. And set that as artboard. I'm also going to instantiate the forest state machine by doing new this.rive.state machine instance. And here, this takes two parameters. It takes a state machine, which I can get by doing this dot or forest artboard dot state machine by name. So similar to how I grabbed the artboard by name, I can grab from an artboard the state machine by a name as well, which should be state machine 1. And it also takes a second parameter, which is the actual artboard itself. So there. And cast that as state machine instance. Missed something here. Oh, I see. I put this in the wrong place. Forest artboard. All right. I'm not going to actually mess with any of the state machine inputs for now. But I'm going to move on actually. No, I want to store these forest artboard and state machine as instance variables. So I'm going to do private just artboard, and private forest state machine as an instance variable as well. State machine instance, because I want to use these in other methods. I'm going to set this dot forest artboard is equal to forest artboard. And this dot state machine is equal to forest machine. Sweet. Now I also want to keep a reference to a layout. This layout is going to be how I lay out the Rive graphics onto the canvas itself. And there's a bunch of options in our help docs around how to format the layout. And those are the same across all runtimes, so you can check more on that. But I actually need to, oh, I already imported layout. Reference to layouts. And the way I create my layout is by doing new layout. This is a class I can create a new object for. And I pass in a fit. So I'm going to do fit.contain for now. Alignment is alignment bottom left. Max x is this dot canvas dot width. And I'll go over that in a minute. And max y is this dot canvas dot height. Okay, so basically what I'm saying is for Rive to lay out the Rive graphics onto the canvas, I need to supply it, how do you want it to lay out on the canvas? Sorry, I think let me make sure it's using my mic again. I think I disconnected. Okay, sorry. I touched my mic and it disconnected. Yeah, do I want to contain all the graphics, the entire artboard on the canvas? Do I want to blow it up so that it takes up the entire space of the canvas while maintaining aspect ratio? These are certain concerns that you want to think about when creating a layout. The next thing I want to do is call this dot resize and reset layout. Uh, what did I put here? Okay, so this resize and reset layout is something that we're going to implement here. Essentially, what I want to do with resize and reset layout when I instantiate this kind of class is I want to give a surface area for that canvas. So if I revisit that page TSX component, um, I've got my canvas element. It's got a ref, but as you can see, I don't actually give it any style attributes. I don't give it any width or height attributes. And so right now, I think it's just going to render at like a 150 by 300 um, canvas space. But really, what I want to do is I want this canvas to take up the entire space um, dimensions of its parent div. And you can see this parent div is um, taking up a bunch of space here. And so what am I going to do here? Um, I'm going to essentially try and set those properties on the canvas element itself here when this class instantiates. So first I want to see, is this dot canvas and this dot container available? And if so, I'm going to create a resize observer. Essentially, I want to check and see when the container resizes. I want to make sure that canvas element matches that parent and scales its canvas area accordingly. And so you'll see what this looks like in a second. I'm going to create that resize observer. I'm going to do this dot throttle 0 milliseconds. I'm going to get the new width of the parent container. So this dot container dot client width, and same thing with the height. So that I can scale the canvas to these new pixel values. So if I do const, I also want to take into account, this is actually super important, the device pixel ratio. I know in the past, a lot of people have kind of mentioned like when they first use Rive, like, hey, when I first created Rive on my website, it looks a little blurry. And the reason for that is because the canvas um, area doesn't have enough pixels to match. I did it again. Just need to stop touching my setup. Um, basically, actually, like on high retina devices, you might have like a device pixel ratio of 2. Basically, what that means is, for example, if you're displaying your Rive on like your MacBook Retina screen, um, it needs more pixel area to efficiently draw all the Rive things on your canvas without looking too dull. And so, for example, on a regular monitor, that device pixel ratio might be 1. On a MacBook screen, it might be 2. And so we want to take that device pixel ratio into account, and we can get that via the window API. So I'm going to say DPR is equal to window.device pixel ratio. And the way I'm going to calculate the new surface area for the canvas is by multiplying the DPR by those new width and height values of its container. So new canvas width is equal to new width DPR. New canvas height is equal to new height times DPR. And say this dot canvas dot width is equal to new canvas width. And this dot canvas dot height is equal to new canvas height. But the actual style property for the canvas, the actual pixels that it takes up on your page rather than the actual pixels inside the canvas, those can remain the same as the container. So I can say this dot canvas dot style dot width is equal to new width pixels. So I don't need to take device pixel ratio into account for the actual style width and height. Um, yeah. And then the last thing I want to do here is this dot layout is equal to, I want to basically change our reference to the layout because now I have new dimensions to work with if the canvas is resized. So I'm going to do copy with and x0, min y is 0, x is the new this dot canvas dot width, and the new max y is this dot canvas dot height. And the last thing I need to do is actually connect this resize observer. And so wait, did I do it to the right one? Oh, this one. I need to do resize observer. Observe. I'm going to observe this dot container, which is the canvas elements parent container. And I'm going to set boxes border box here. So essentially all I did here is just whenever the page resizes, which the div is going to be taking up the space for, I want the canvas element to scale with it. And so in this case, that's how you can make it a little more responsive. This is actually what happens underneath the hood for the React runtime. In the React runtime, it does this a little more optimized, but for this purpose, it's probably fine. And whenever you scale whenever you change the width or height of your viewport or anything like that, you may notice if you use the React runtime, it all just scales for you. This is really what's happening behind the scenes. It's using a resize observer to scale the canvas accordingly because it unfortunately won't do that for you automatically. So again, that's what we called at the end of our initialization. One other thing I want to go over here is, I'm going to actually implement this resize drawing surface to canvas. And in this case, what I'm doing is, am I actually using this? Resize drawing surface. I'm going to be doing the same thing here in that I want to set the new width and height attributes on the canvas element and essentially create that new surface area. And we'll be using this in the render loop. This actually might not be needed, but just in case. So I'm going to set that canvas.width is equal to dpr dot times the width. And this dot canvas dot height is equal to dpr times height. Okay, what do I want to do now? Let's actually go and build the render loop. So I've got this async run method, and we're going to be calling this from page TSX once everything initializes. This is the thing that we're going to be calling that like actually displays Rive and is actually this render loop is going to be recursively called every frame using request animation frame to actually advance the animation and state machine over time. And so with this, I want to have a reference to my last time or the times of the last frame. So I'm going to just create an instance variable here called last time. If last time is not available, this dot last time is equal to time. Essentially, why I want to keep a reference to this last time is I want to get the elapsed number of seconds between the time that initial frame ran and when the next frame comes running around and we're ready to draw again. I want to know the amount of time I need to advance the state machine and artboard. Uh, and that's really what drives our animation. And so we need to kind of track two times. One is the time elapsed, the new time of the next frame, the time of the last frame. Subtract those two, get the difference, and that's the difference that I'm going to be animating or advancing my state machine, my artboard of the forest, the bears, everything. And so we'll see what that looks like in a second. So I'm going to get that elapsed time, like I mentioned. The elapsed time in milliseconds is minus last time. These are all milliseconds, by the way. And with Rive, I need to advance things in terms of seconds. So I'm just going to convert that. So const elapsed time is seconds equal to divide that by 1,000. And I want to keep a reference to the current frame so that the next frame knows what time I ran. This dot last time is equal to time. Excuse me. Okay, so now we get into the kind of the cadence of how you build a render loop. And this is, I know we just went through a lot of hoopla, like 50 minutes, but this is kind of the crux of and the power of building and advancing things in your own control. And so um, you can, for example, with this render loop, you can advance state machines and artboards like 2 times their elapsed value, thus making the animation basically go twice as fast. You can do the same thing where you do elapsed time seconds divided by 2 when you're advancing these state machines and make animations go twice as slow. Uh, for our case, the way that we start the render loop is by doing this.renderer.clear, which is going to clear the canvas for that frame. And then it's going to, we want to basically animate our things. And so I've extracted this into its own function, but we'll implement that in a bit. So we'll do animate forest, and we'll pass it elapsed time seconds, and we'll go over that in a second. And then we're going to call this.rive.request animation frame the render loop. So you can see here, I'm actually passing in the function that I'm currently in as the callback. And so what this is going to do is once this render loop runs, this request animation frame is going to request the next frame. It's going to call render loop again with the time of the next frame that it's going to render at, and just continuously loop this. And the magic that we're going to include here is this .animate forest. And I'm going to try and go a little faster here just for time purposes. So animate forest, look at my notes, takes elapsed time seconds, which is a number. And what I want to do here is I'm going to advance the state machine. So forest state machine dot advance, and I'm going to pass it that elapsed time seconds. Because again, Rive, when you advance the state machine, the artboard, it takes a number of seconds. And really what I mean by advance is if we go back to the editor, you can see, I don't know, I'll go to like a random timeline. I'm trying to see how much do I advance this kind of playhead by. And so that's what you can kind of think of it as, like every frame of the render loop, you can think, okay, it's at this frame. I want to draw what's at this frame for the artboard, and I want to advance the state machine at, give it that current time as well. And when it recursively calls that render loop again in the request animation frame, it's going to, for example, maybe go to this frame. And then it gives me the elapsed amount of time since that last frame was drawn. I want to supply Rive with, hey, we're at this frame. I want you to go draw however many seconds, is maybe like 0.1 seconds or something. And so Rive will go ahead and interpolate all those values up until that next frame that the playhead is at. And the playhead is really that second render loop recursive call. So it's a little hard to visualize, but essentially what we're doing is every frame you can imagine, we want to say, hey, we want to tell Rive, hey, this is how much you should advance the playhead by, interpolate all the values in between that so that you can show that animation over time on the canvas. And so that's what I really mean by controlling the render loop. This is what it's doing under the hood, and the high level runtimes for all our runtimes that you usually don't have to control yourself is it's just continuously advancing animations by a certain elapsed time. And it does that for one canvas. In this case, we want to include everything in one canvas. It's a little more efficient. We can procedurally create all these bears dynamically. And these are all instances of the same artboard. And so that's really another nice benefit is you don't have to have these all as separate canvas elements, which include, um, you know, their own Canvas 2D context. If you use the high level runtime to do something like this, you could, but really what you'd be doing is having a Rive instance for each of these, which creates their own canvas element, which creates, which means recreating the Rive file, the artboard, reinstantiating all of that. It's a little costly. It can be costly for at least this kind of thing. Um, if you've got like dynamically created, artboards and a bunch of animated assets on stage, like this is using the low level runtime, controlling your own render loop is really going to be a lot more efficient. Um, Not only for space, but it just like taking up memory, all those things. It's like it's just going to make things a little easier on you when it comes to performance and debugging if you're continually adding more animated assets here. So uh, that's really what we mean by advance. So I advance the state machine. I also want to do the same thing for the artboard. So I'm going to do this dot forest artboard dot advance last time seconds. For the forest, I want a different layout. I want the layout to be covered, which means takes up the entire canvas while maintaining the aspect ratio. So I'm going to do layout, layout dot copy with fit cover. And I want it to align at the bottom in the center. Um, Now the next thing is I want to call this dot align artboard. I'm going to pass this, and we'll implement that. Next is my forest art, my actual artboard that I'm going to align. And a temp layout. And so what the purpose of this artboard, this function is going to do is the render is going to take into account my layout for this and draw accordingly. So this takes, what is it, artboard, and layout is a layout object. So the first thing I'm going to do here is I'm going to do this .renderer.save. A lot of these APIs come from the Canvas 2D context APIs themselves directly, so this should look familiar. So backing up again, the first thing I did in the render loop is I did this .renderer.clear, which clears the entire canvas. Excuse me. And then I'm saving the state of the canvas via this .renderer.save. And I'm not going to go over too much of like what that entails, but those are available on the web. You can check any website for the web APIs for Canvas 2D. So like the Mozilla website as well. I'm going to do this .render.save. Now I'm going to do this .render.align. And what this does is takes the fit and alignment as well as your bounds of where you want to draw to. So like the min x, max y, max y. and the artboard bounds and tries to fit the artboard onto the bounds of which you supplied. And so that'll look I didn't explain that well, but that'll make sense in a second. So if I provided a layout, I'm going to use that. Otherwise, I'm just going to use this dot layout. I'm going to use runtime fit. Um, so this is essentially how I'm supplying the fit of my layout. I'm doing the same for alignment. The second parameter, like I mentioned, are the bounds that I want to draw to. So min x is this dot layout dot min x. Um, actually, here use out here. All right. And then the third parameter is, you can see here, it takes an AABB. This is similar to what I just provided, but I'm going to provide it from the artboard's perspective. So I need the artboard bounds. In this case, I have the artboard passed in here, so I'm just going to do artboard.bounds. Right now it's all happy. And so what I'm going to do now is I'm going to do artboard.draw, and I'm going to pass it this dot renderer. So this operation, oops, when I pass the renderer to this artboard.draw method, this is where Rive takes the renderer, uses the paintbrush essentially, and draws it onto the canvas. And so this will actually get something displaying on screen. This dot renderer dot restore. That will kind of close out the loop. And so essentially what I've done here is I've saved the state of the canvas. I'm going to draw my frame of the artboard, so the forest, and then I'm going to restore the state of the canvas back to its original state. Okay, and so I think, oh wait, what is this? Temp layout. Oh. Okay, so I think this should be good enough for me to actually build something or run. I think I got some CSS variables mixed up though, so let me just change that real quick. And if I run this app, which I've done, I think it's at localhost 3001. Okay, so got that loading percentage here. Oh, because I didn't actually instantiate the class. I'm going to go back to my page component and actually instantiate that Rive Bear scene that I've been working with. Ref. Okay. If canvas ref dot current and canvas container ref dot current, I'm going to create my bear scene. Oh, yeah, my bear scene. And I need to make that into an async function. Now I'm going to actually create that scene. So ref bear, I guess I'll call it Orchestrator. Yeah. And again, this takes the canvas and its container. So I'm going to do this canvas ref dot current is container, oh, canvas container ref dot current. I'm going to initialize everything by doing bscene.init and bscene.run. Okay. Oops. Wrong variable there. All right. So let's see what's going on now. So I did right. Let me make sure it imported Orchestrator from components. Yep. I initialized everything. What am I missing? Oh, and in my initialization, I might need to before I instantiate the layout, I need to do this dot resize drawing surface to canvas. What's missing? Oh, I didn't actually call this. I didn't actually do the initial call to render loop. So I do request animation frame render loop here. Okay, and now we've got a forest loading finally. And you can see over time it's animating each of these frames. And so, yeah, we've got that going for us. Right now, I didn't implement listeners. With the low-level runtimes, you have to kind of include the listeners yourselves. And I might go over that a separate time. But let's actually add the bears now, which is the more interesting part of this. So to start with, I want to create a type for the bears. For each bear instance, I want it to have like the artboard, the state machine, whatever, and I just want to maintain a set of them so that I can uh, dynamically create them, insert it into the set, also dynamically take it out of the set if the bear goes off screen. So I'm going to create that type here. Artboard is artboard. It has an artboard. State machine instance type. I'm going to also create a reference to the walk type state machine input. So walk type is SMI input. I need to import that SMI input here. And I want to also maintain for each bear its position. So this is just a number. This is X position is a thing that I'm going to be incrementing over time in that render loop. And we'll see kind of, that's how we get kind of the artboard to move across the screen. So the first thing I'm going to do is I want to actually create an add bear method and handle all of this for me. So I'm going to do artboard is this dot bear file. Yeah. Artboard by name. And the artboard name for the one I want to use is called different walks main. And the state machine is this, new this dot rive dot state machine instance. And the first parameter again is the artboard dot state machine by name. In this case, it's also state machine one. I also pass it in the artboard as well. And I also want to get the walk type input, which I want to make random because I want to have the random different poses of the bears. So I'm going to do let I is equal to 0, I is less than. I have to iterate over all the state machine inputs here. So I'm going to do so That's weird. How to complete something weird. Um, all right, so in my state machine, I can iterate over all my inputs, find the one I need. In case, there should only be one, but it's just good practice to iterate over and specifically call out the one you need. So I'm going to do if input.name is equal to walk type. I'm going to set walk type input.as number, making sure that I'm casting it basically as a number input. And I'm going to do walk type.value is equal to um, a random number between, for the bears. Again, if we look back at the state machine, there's an enumerated number of walks from 0 to 5. So I want to create a random number from 1 to 0 to 5. So I'm going to do math.floor random times 6. This will give me a random number from 0 to 5. All right. And now that I've created a bear, I'm going to add it to a set. And so I'm going to just maintain a private instance variable here for the set of bears. I call this bear sets is a set of bear instance. New set. So I'm going to do bear sets dot oh wait, this dot bear sets dot add new artboard, the state machine, the walk type, and the x position, which I'm going to start at negative 550. All right. I'm going to now create the animate bear function. So similarly, how we created the animate forest function, which advanced the state machine and artboard and all that good stuff, we're going to do the same thing for the bears. So if I go down to this, I'm going to assume I have a bear. So I'm going to grab the artboard, the state machine, and the X position from the bear. And I want to advance the state machine. I should pass in seconds. I'm going to advance the artboard by the same elapsed number of seconds. And to actually align the bears to the bottom of the canvas rather than the top, which is what it would probably do automatically, I need to set the min y and max y for this layout for the bear. So I'm going to do temp layout, layout.copy width. So I'm going to make a copy and just change the min y value to this.canvas.height. And it's like 300. Canvas.height is the max y. So this ensures that the layout, when rendered, is at the bottom of the screen, the bottom of the canvas. Right. And now I'm going to actually align the artboard here. So this dot align artboard, the artboard. Out. And actually, I'll also pass it the bear instance. I want to change the X position here. So bear instance. And if there is a bear when I'm aligning the board, I'm going to do bear um, dot x position is equal to, I just want to increment it by 5 every time. And then I'm going to take the render and translate that bear to draw where I want it to. So I do this. Basically, what I'm saying is, hey, renderer, go move the paintbrush to the bottom of the screen where the X position is, um, and draw it. And so I'm just using some translation here to draw the bears accordingly. Okay, so now that I've kind of like got the methods for animating the forest and the bear, I'm going to include that in my render loop by doing bear sets that for each bear, this dot animate bear, and this takes my bear instance as well as an elapsed number of seconds. Right now, if I play this, we should have some bears coming on screen. Oh wait, actually, I actually need to add bears. So I'm going to go back to my page component, and I'm going to use a random interval, uh, which is a random. It's a utility function I have, which essentially just every random interval between like 1.5 seconds to, for example, like 4 seconds, create a new bear for the scene. So it's like a regular set interval, but kind of modified here. So I'm going to do scene.add bear to the scene. And I want to do this every somewhere between 1 to 3.5 seconds. So, okay, we've got it animating, or at least getting on screen, but it's not actually moving. And the reason is, what is the reason? Let's see. This dot render dot translate bear. What am I doing? Bear dot x position plus equals 5. This dot render dot translate. I'm telling it to go to the bear's new position. And I draw. What did I do wrong? Why are you not animating across the screen? What? This is funky. So bear dot x position plus is equal to 5. And then I'm translating the bear's x position. Am I missing something? Okay, so I've got my max y is, it's rendering in the same, it's rendering fine on the Y part. It's just the X that's kind of funky. Uh, Maybe this isn't actually incrementing. Let me see. Oh, I didn't actually pass in the bear. Okay, I think I got it. There we go. Okay, that was dumb. Console. Um. Okay, so what I had done wrong was I I I have that function align artboard. This is really where I align like the layout with the artboard bounds and things like that, and actually draw the artboard onto the canvas. And what I added here in this shared align layout, align artboard function was this third parameter bear, where if bear was passed in, increase the X position by 5. So this happens like every frame. And then I tell the renderer, hey, go draw to that next X position, basically telling it to move the artboard um, along the X axis. Cool. Okay, so that's kind of the crux of it. We've actually got uh, randomly generated bears between 1 and 3.5 seconds, kind of just strolling along the bottom of the screen here. And they should be random. I think some of the walk cycles look very similar, but you can see here it's got like some happy ones, some angry bears walking along the screen. And so you can see this is kind of like the power of building your own render loop. You can instantiate multiple artboards, however many you need, all from one Rive file. So you only had to load in the Rive file once, create multiple instances of this artboard. This is also a very similar technique, very similar techniques to how you would use the Rive game kit if you're familiar with that. Um, and we're using the renderer to basically align the Rive content accordingly. So we're using the renderer to draw and cover this forest artboard and state machine to the entire canvas. And meanwhile, we're telling the renderer to draw the artboards on the bottom of the canvas, only with a certain height, and move along the x-axis accordingly every frame. The one last thing I want to include here before we sign off, and I know it's been kind of a long, uh, drawn out live stream here, is making sure that we clean up our resources. And this is important because you probably saw it just as like a minute ago. If I keep this page running, what it's continuously doing is it's continuously generating, whenever I create these dynamic artboards and state machines and adding it to that set for each of these bears, it's creating new C++ objects constantly. And advancing those over time. And if I leave this running for so long, the browser can only handle so many resources, and I'll actually run out of memory. The page will crash, and that's because I haven't cleaned up any resources. I'm just continuously generating CPP objects. And so what I want to do now to um, kind of finish out this live stream is show how you clean up these resources. So for example, once the bears walk off screen to the right, I want just clean up those bears, remove them from the set because I don't need to advance them anymore and I don't need those CPP resources. And when I clean these up, I'm going to actually delete those CPP objects so that I'm not just continuously building up memory usage here. So what I'm going to do here is I have this clear off-screen bears method. I'm just gonna keep a reference of bears to remove in an array. So bears to remove this instance. And I'm going to iterate over my set of bears. And I'm going to say if bears x position is greater than the canvas dot width times 2, which is a fair amount, I'm going to say I'm going to clean up all those CPP objects. So the simple way I have to do that is just bear.artboard.delete, and also bear.statemachine.delete. So these are all CPP objects that are generated. Some of them you don't actually have to delete, like the state machine inputs. Um, but the artboard, the state machine, the Rive file, when it's complete, those are all necessary to delete. In this case, because it's just a continuously looping thing that's always generating uh, these artboards and state machines, I don't want to delete the Rive file. I'm going to set bear.exposition equal to -1 for good measure. And I'm also going to add to bears.remove the bear instance I want to delete. Now I'm just going to iterate over bears to remove and say this.bear sets.delete bear instance. Um, yeah, I won't keep the site trying to go so long so that you can see the actual crash or not crash here, but this is the approach you want to do when you are kind of cleaning up any animated instances that you don't need anymore. So this is useful, like cleaning up things. For example, if you've got an animated asset that has finished, um, then you do it basically by finished, like it goes into its exit state or something, and it's not going to animate anymore. And perhaps the user has scrolled past the animation down the page or for something like that. Then you can clean up and delete these instances if you're using the low-level runtime. Using the high-level runtime, there's a really nice, convenient API for you to use. In the help docs, it mentions the dot cleanup. And that's just a single line API that you use, and it'll do all of this for you. It goes through all the instances that it has created for that Rive instance. So all the artboards and state machine that was associated with that Rive instance, and it cleans that up as well. And then the last thing I want to do is actually call that here. So after animating all the bears, I want to do this dot clear off screen bears. And oh yeah, you can see here that it crashed because I just kept it running too long. But if I kept this running, now it should only clean up bears once they've passed the threshold of um, the canvas width times 2. So basically anything off screen. And yeah, anyway, that's the long stream. It went a little longer than I intended. Ran into a few hiccups from what I actually implemented, but this is the general gist for a loading screen idea that you could use using the low level runtime. And even though they're only available on the web, plain JavaScript, TypeScript APIs, you can still use them in React, as you saw. I created this kind of orchestrated class here called the Rive Orchestrator, and just use that in a use effect block in one of my components, and instantiated it that way. So I think that's all I'm going to include for now. If you have any questions, if anything was really confusing, and I'm sure I might have not done the best job of explaining some of these things, you can leave a comment below. You can join our Discord community from our Rive app website and join the conversation there if you have any questions using the low-level runtime. I'll also include the code snippet or the code for this project shortly after this video is published, so you can check it out yourself and kind of digest on your own time, as well as the Rive assets that I used for building out this experience. And yeah, hopefully we'll see more usage of the low-level runtime. And if you find this interesting but want to use a different runtime, I'm sure there's a path to use that as well for whatever platform you're building on. So, all right, I'm going to stop sharing, and thanks for joining in, everyone.